Alright, welcome to this video. We're going to start talking about phase equilibria of pure substances, right? And so in this video and a number of following videos, we're going to be talking about phase equilibria and eventually some chemical reactions and other things of that nature, okay? And we're going to use a lot of the topics and concepts and ideas we've discussed with enthalpy and internal energy and Gibbs free energy and such in these videos and in future discussions, right? We're going to start now applying a lot of these ideas that we've been talking about to things besides compressions and expansions of gases and such. All right, so chapter 4 again is just dealing with phase changes for pure substance only. Okay, so we're not going to deal with mixtures of things. We'll deal with that in future discussions. Okay. And the main principle behind any phase change that's occurring is that your system is trying to minimize the chemical potential to obtain the most stable phase, right? Again, remember, this chemical potential under constant temperature pressure conditions is related with the change in Gibbs free energy with respect to change in number of moles, right? So if you change your moles from a liquid to a gas, and during that change, right, you go to a lower free energy, right? This has a free energy change that's less than 0, right? This is a spontaneous reaction, right? And it's a spontaneous reaction, right? And this occurs, right? This is less than 0 only if the chemical potential here is greater than the chemical potential here, okay? Right? So you're trying to minimize your chemical potential, okay? So that you can minimize your free energy, right? This chemical potential is related with the molar Gibbs free energy under constant temperature pressure conditions, right? And so let's consider, right, there's some concept ideas, right? For phase, we're talking about solids, liquid, gas, right? And the phase, everything is in the same phase for your system, right? But even chemical composition can actually refer to a phase. We talk about mixtures. Talk about mixtures of two things, right? That in liquid phase versus a mixture of two things in gas phase. Okay. You have common phases or solids, liquids, and gases, right? Solids can have multiple forms, right? Multiple types of solids. Carbon can have like graphite and diamond, for example. Okay. And again, when the phase transition occurs, you're essentially just going from a higher chemical potential phase to a lower chemical potential phase, right? So if I look at the temperature dependence of this chemical potential, right, we have 3 different chemical potentials here: the chemical potential of the solid, right, the chemical potential of the liquid, okay, and the chemical potential of the gas, right? And these all 3 vary with temperature, and they vary with temperature in different ways, right? And the phase change occurs only when right, these 2 chemical potentials become equal to each other, right? And then as you are trying to increase the temperature here, right, you go from the solid to the liquid phase, and then you go from the liquid to gas phase at this point here, right, where the gas phase chemical potential starts to become lower than the liquid phase chemical potential. Okay. So, right, these transition temperatures, transition in which these phases occur, right? The temperature in which these transitions occur between 2 phases, right, is the temperature in which these 2 chemical potentials are equal to each other. Okay, right, and those phases are then at equilibrium, right? And so this will pop up again with chemical reactions and things like that, right? That equilibrium occurs when the chemical potentials between different phases, between your reactants and products, right, are equal to each other. Okay. So, right now, even if some phase is more stable, you can have something exist in a metastable state, right? Again, an example of this is diamond is technically a metastable form of carbon, right, at room temperature pressure conditions, but again, the transition from the less stable to the more stable phase can be, doesn't necessarily have to happen quickly or really at all if the barrier is just too high. Okay, right. So again, that transition from diamond to graphite is a thermodynamically favorable transition, but a kinetically impossible transition. Okay. So we'll talk a little bit about phase diagrams. Hopefully some of this is a review from other chemistry classes, right? You got your phase boundaries, right? The separations between your two phases, you know, solid liquid phase boundary, liquid vapor phase boundary, okay? Right? Now, the nice thing about these phase diagrams that maybe you haven't talked about before is that you can read off from these phase diagrams the vapor pressure of a liquid at a certain temperature. Okay, so if I have a liquid at some temperature here, its vapor pressure I can just read by drawing a straight line up to this phase boundary and then going over to the pressure, and this is going to be the vapor pressure of that liquid at that temperature, right? So the phase boundary between this liquid and gas tells you, right, how that vapor pressure changes with temperature, right? Similar, the sublimation pressure is related with the solid, right, to gas phase boundary, where again you can read off the vapor pressure of that solid from the phase diagram. Okay. Right. Our normal boiling point, right, is the temperature in which your vapor pressure is 1 atmosphere, right? Your standard boiling point is when that vapor pressure is 1 bar, okay? So let's pretend here this is like 1 bar, right? The boiling point of this liquid then is going to be at temperature down here, right? Okay, and again, you can just read that off from these phase diagrams by just kind of drawing these straight lines from different temperatures to pressures, okay? Right, the critical point is out here. Critical point is kind of the temperature pressure conditions where the liquid and vapor phases, the difference between them kind of disappear and they become a single phase. Often these are referred to as still just kind of a vapor gas phase system beyond the critical point, right? So beyond this critical point, right, you kind of consider things as just gases, okay? Right, now you can call it supercritical fluid, but it's basically considered a gas, okay? Right, normal freezing points, again, you can get from your phase boundary, right? You look at your pressure, drop down the temperature, right? And you get your freezing point by reading off the temperature, right, at 1, you know, bar worth of pressure, for example. Okay, the triple point on this curve, right, is the point in which all 3 phases are in equilibrium. It's a single temperature pressure point. Okay, for water, it's at 273.16 Kelvin and 4.58 torr. Okay. Typically, for most substances, the triple point is the lowest pressure and lowest temperature in which a liquid can exist. Okay. Now, this isn't true for things like water, potentially, but in most cases, triple point is the lowest temperature pressure conditions in which the liquid phase exists. Okay. So again, if I want to interpret my phase diagram, right, I want to know what is the boiling point at 1 atmosphere, 0.5 atmospheres, 1.5 atmospheres, right? For water, again, I draw a straight line, say from 1 atmosphere, draw down, and read off that temperature, okay, right? If I want to know what it is at, 1.5 atmospheres, go over, find that point phase boundary, draw it down, say it's now 400 degrees Celsius, okay? Let's say I want 0.5 atmospheres, go over, draw down, right? Let's say it's now at 325 degrees Celsius, right? So to find these vapor pressures, right, you just do that, draw a straight line, find the phase boundary, and go straight down from there, okay? Right? And then again, finding the equilibrium vapor pressures is just doing the opposite, right? Doing equilibrium vapor pressures, right, starting at your temperature that you want, right, go up, and then go over to read off the vapor pressure of that system, or of that liquid at that temperature, okay? Right, now note, most cases, right, like every system, the solid liquid boundary is typically a very steep slope, okay? Now, notice for water, it's a negative slope, which means that, and it's due to the density of ice is less than that of the liquid form, right? And so because of that, you have this negative slope, which then causes an increase in pressure, right? Means, right? So if I increase pressure, okay, the freezing point actually decreases, okay, in terms of temperature, which is opposite of most substances, okay? Right. Now, water is an example of a substance that can have many forms of solid form, okay? But if we look at this phase diagram, you will never see more than 3 phases in equilibrium with each other. So there's multiple triple points, say, between these different solid phases, potentially, okay? But you never have more than 3 phases in equilibrium at once, okay? So you can have more than one triple point, okay? But you can never have, for a single substance, you can never have more than 3 phases in equilibrium at a time, okay? Now, the relationship between the number of phases you can have in equilibrium, right, is given by this phase rule, okay? So F is your degrees of freedom. Your degrees of freedom are the number of things you can change arbitrarily and remain in the same phase or phases that you are currently in, okay? C is the number of components for a pure substance, C equals 1, right? And P is the number of phases in equilibrium, right? So for example, if I'm just looking at the gas phase, right, for a single component system, C is 1, P is 1, so I get 1 minus 1 plus 2, F is 2. F is my number of degrees of freedom, right? I can remain in the gas phase by and arbitrarily change temperature and pressure, right? And that holds true, right? In the gas phase, I can change temperature and pressure of my gas and still be in the gas phase, okay? But now let's say we look at the solid or the liquid gas boundary, okay? Well, now I have 2 phases in equilibrium, so P is 2, C is still 1, right? And so now my F is equal to 1, okay? That means that my number of degrees of freedom is 1, which means I can say vary the temperature of my system arbitrarily and still remain in equilibrium between the solid or the gas and liquid phase. But to do so, I have to change the pressure, right, the external pressure on my system accordingly to that phase boundary. Okay. And then if I have 3 phases in equilibrium, right, that's the triple point. P is 3. I have C minus 3 plus 1 minus 3 plus 2, which gives me 0 degrees of freedom, which means, right, there's just a single point in space where all 3 phases are in equilibrium. I can't change temperature or pressure at all to remain in equilibrium between all 3 phases, right? And then F would be negative if the number of phases in equilibrium were greater than 3, okay, which is not possible. I cannot have some negative number of degrees of freedom. The smallest number of degrees of freedom I can ever have is 0. Okay. Right? So just looking at some more phase diagrams, right? Okay. Right? We can look at, say, where the triple point is for water, or for carbon dioxide, which we see is at 5.11 atmospheres, right? Which is much greater than the 1 atmosphere that we live in most places, right? Which is why, right, water or carbon dioxide sublimes, right, why you have dry ice, right, why that goes straight into the vapor phase without forming a liquid, because you're below that triple point of carbon dioxide, okay. Right, and some more interesting phase diagrams are things like helium, where you can have different liquid phases, where you can have a normal liquid phase of helium, and then what's considered this other liquid phase of helium, which is considered a superfluid. Okay, this superfluid is a fluid that flows without any viscosity. There's 0 viscosity for this thing, right? You can see if you look at the superfluid of helium, it will rise up and go over any wall in a container and things like that due to gravitational forces pressing on it and other things like that. And so it's a very unique fluid. Okay, but it has 0 viscosity, which is, that's why it's called like the superfluid, because that's not really typically what happens with any liquid having 0 viscosity. Okay. Right. So I'll talk a little bit about what is the thermodynamic criterion for something to be at equilibrium. Okay. And again, that is related with the chemical potential of those 2 phases being equal. Right. Okay. So again, under constant temperature pressure conditions, right, that chemical potential is related with change of Gibbs free energy and change in number of moles, right? So let's suppose I have two chemical potentials, mu1 and mu2, in two different phases, right? Right, some change in the number of moles from one phase to the other, right? Transferring from phase 1 to phase 2 corresponds to a change in the Gibbs free energy related with the difference in those chemical potentials times the number of moles you've transitioned between those two phases, okay? Now, if you're at equilibrium, right, there will be no net change in Gibbs free energy with the change in number of moles because the chemical potentials are equal, right? Equilibrium implies dG equals 0, okay? Which dG only equals 0 if mu1 equals mu2, okay? Right? So again, at equilibrium, the number of moles of, say, liquid going to gas can change, right? I can have a bunch of moles going from liquid to gas or a bunch of moles going from gas to liquids. The free energy of that entire system does not change during those transitions between the two phases, right? So they're in equilibrium, and I can freely transition between the two phases at will. Okay. Right? So again, we talked about the temperature dependence, right? We can formally show what that temperature dependence is by remembering, right, that the Gibbs free energy is related with change in pressure and change in temperature. So under constant pressure conditions, right, that Gibbs free energy is just related to entropy, okay? Well, the chemical potential is just that molar Gibbs free energy, right? So G divided by N equals mu, okay? And so we get the molar Gibbs free energy in here, and then the molar entropy in here, right? So the change in chemical potential with respect to change in temperature is just related with the molar entropy of that substance, right? So that slope increases with the entropy of the substance, right? Which is why the gas phase has the greatest slope out of all of these, because it has the greatest molar entropy. Okay. And then notice here, because this built-in negative, right, that the chemical potential always decreases with an increasing in temperature. Okay. And again, the relationship between these slopes is related with the molar entropy of those different phases. Okay. Now, to get how melting is affected by pressure, right, we look at how the Gibbs free energy changes with pressure, assuming constant temperature conditions, right? We get this relationship that the change in chemical potential with respect to pressure under constant temperature conditions equals the molar volume, okay? And so if you have some isothermal system where you're plotting the chemical potential, right, versus pressure, okay, that slope would be equal to the molar volume, right? That's not what's given here. Right here, I have chemical potential, okay, versus temperature, right? And so what I'm just looking at, right, is the fact that, right, at some constant temperature, right, if I increase the pressure from this low pressure system in the black curve to the high pressure system in the blue curve, right, my chemical potential increases, okay? Right, and then that increase in chemical potential for a liquid versus a gas is different, and so that will change where the boundary is, right? So initially, the boundary, the low pressures, right, where these things match up, the equilibrium point is here, right, as I increase the pressure because of how these things change differently, because the molar volume of the liquid and the molar volume of the gas is different, okay? That boundary, that phase boundary shifts to higher temperatures. Right. In the bottom, we're looking at the liquid to a solid, right? Right. In which case you have the phase band, the transition temperature decreasing, okay, because of the fact that the liquid has a much greater molar volume compared to the solid typically.